At last, we are ready to study the famous Q-learning algorithm. Let's recap what we've done so far, because it's been quite a long process to even get to Q-learning. First, we defined all the relevant terms, such as agent, environment, state, action, reward, and so forth. Having these definitions allowed us to structure our problem mathematically. Specifically, we can model reinforcement learning problems as MDPs, Markov decision processes. Next, we considered how we would solve an MDP, meaning two things. First, we solved the problem of prediction, finding the value function given a policy. Second, we solved the problem of control, finding the best policy in a given environment. We learned that if we know all the probabilities in an MDP, this is quite easy. But when we don't know the probabilities, we can use sampling methods, which we call Monte Carlo. There is one major problem with Monte Carlo. It is that in order to calculate returns, we must wait until an episode is over. This is because the return is defined as the sum of all future rewards. We can't know the sum of future rewards until we have collected them, and therefore we must reach a terminal state before calculating the sample returns. Why is this a problem? Well, imagine the scenario where you have very long episodes, or the scenario where there is no terminal state. In the latter case, Monte Carlo is not an option. In the former, it's still not ideal, because that means your agent has to spend a very long time performing suboptimally, even though it has already collected a lot of data from which it may improve. The answer to this is temporal difference methods. If you recall, I said earlier that one of the most important features of the return is that it can be defined recursively. The return at time t can be expressed in terms of the return at time t plus 1. You saw how this helped us both create and solve the Bellman equation. Now it's going to help us once again. One simple way to think about it is this. Monte Carlo methods were an approximation to an expected value problem. Temporal difference methods are simply an approximation to Monte Carlo. So in other words, they are an approximation of an approximation. Recall this one neat trick with Monte Carlo methods. When we're updating Q or V, which is the sample mean of all the samples we've collected, we don't have to express the update as a sample mean. That would mean we have to keep all the samples around, which can take up lots of memory and take lots of time to calculate. Instead, we can express the current sample mean in terms of the past sample mean. We noted that this looks a lot like gradient descent. Well, why not test out this theory? Let's set our squared error j to be the squared error between my true target g and my value for the state s v of s. Now let's say I want to update v of s using the latest sample g, which I've just collected. In order to perform the update, I'm going to use gradient descent. Set v of s to be the old value of v of s minus the learning rate times the gradient. Well, what is the gradient? If we plug this gradient into our gradient descent update and ignore the 2, since it can be absorbed into the learning rate, we get back the exact update equation we would use for the exponentially decaying average. As a side note, I want to mention that there is ultimately no difference whether we call what we are doing gradient ascent or gradient descent. Because there's a plus sign here, you might think of it as gradient ascent. The plus sign is natural to use if you derive this expression from the sample mean update. But if you derive this expression from the squared error, you will get a negative sign, and you might think of that as gradient descent. Ultimately, however, this is just basic algebra, and you should confirm to yourself that both expressions are equivalent. So what's so significant about this? Well, now we're going to put together these two ideas. Idea number 1 is that updating the value function using the exponentially decaying average is just like gradient descent. Idea number 2 is that the return can be defined recursively. So how about this? We're going to continue using gradient descent, but instead of using the full return, we are going to estimate the return. We collect the next reward R, but instead of waiting to collect any future rewards, we simply guess that they will be close to v of s prime, the value of the state where we landed. So instead of using g equal to r plus gamma times the next reward plus gamma squared times the next reward and so on, we recognize that g is just equal to r plus gamma times the next return g prime. But g prime has the expected value v of s prime. So we instead just say g is approximately equal to r plus gamma times v of s prime. In this way, we only have to wait one step before updating our model. We no longer have to wait until the end of the episode. We call r plus gamma times v of s prime a bootstrapped estimate of the return. It allows us to update v of s immediately after obtaining the next reward r, instead of having to wait until we've collected all the future rewards. This method is called the temporal difference method. Here's some pseudocode so you can conceptualize how this will work. As a side note, this should also give you some insight into what goes on inside our play episode function, which we haven't really discussed yet. In this pseudocode, we don't have any need to abstract away the play episode function, because playing the episode is part of this loop. We have things to do on each step of the episode, and therefore, we cannot encapsulate it or delegate it to some other function. To start, assume we are given some environment and some policy. We initialize the value function to be random. Then we enter a loop which plays a predetermined number of episodes. Alternatively, you could also run the loop until you find that v of s converges, or in other words, settles on some value and doesn't deviate from it. Inside the loop, we begin playing an episode. The first thing we do is call env.reset, which resets the environment and puts us back into the initial state and returns that initial state. We'll call it S. Next, we initialize a done Boolean flag to false. This Boolean flag will get set to true when we've completed an episode. Next, we enter a while loop that completes when done becomes true. Inside the loop, we grab the action from our policy. We then perform the action in the environment by calling env.step. This returns three things: the next state s prime, the reward r, and the next done flag. Note that I've designed this pseudocode to be similar to the OpenAI Gym API, which has become somewhat standard over the past few years. It's easy to understand, and it will help you in the future if you ever do start using OpenAI Gym. The reverse is also true. If you've had experience with OpenAI Gym in the past, this should make things easier to understand. Next, we do the big update, the temporal difference update we've been discussing throughout this lecture. Finally, and this is important not to forget, we must update the variable s for the next iteration of the loop. What is currently the next state s prime will become the current state s in the next iteration. Lastly, when the loop is complete, v of s has converged. There is one odd thing about temporal difference learning. Look carefully at this so-called gradient descent update. The target is r plus gamma times v of s prime. The prediction is v of s. If we relate this back to supervised learning, we notice something strange. In supervised learning, we are given the target as part of the dataset. But here, we are doing something surprising. We are predicting the target itself. Part of the target is given, that's the reward r. But the other part, v of s prime, is actually a model prediction. Thus, it's more correct to say that what we are doing is not quite gradient descent. It's called a semi-gradient instead. But this is just a name. It is the principle that's important. The principle is we don't know the true target, we are estimating it. And this makes it very different from supervised learning. Alright, so what we looked at so far was the prediction problem. Now it's finally time for the big reveal. We are going to solve the control problem using the famous Q-learning algorithm. At this point, we've spent so long building up the prerequisites for Q-learning that you should hardly be surprised at what you see. Nonetheless, let's have a look. As before, because Q-learning is a control algorithm, we are interested in updating Q rather than updating V. At a high level, we are mostly interested in the innermost part of the loop. That is, where we choose an action and take a step in the environment, and where we update the Q table. So these are the two pieces we are going to focus on here. When we choose an action, we are again going to use an epsilon greedy approach. So with small probability epsilon, we will choose a random action. Otherwise, we'll take the argmax over Q given a state S. Once we choose our action, we then take that action in the environment. When we update Q, we do something very subtle but important. That is, when we calculate the target, we ignore whatever action we are going to take next. Instead, we assume that we will take the greedy action and take the max over Q given the state S prime. This has two advantages. First, it means that in order to update Q, we don't have to wait until we obtain the next action A prime in the next iteration of the loop. Second, it makes Q-learning what is called an off-policy algorithm. This means that I can freely explore, but my algorithm will update the Q table as if I had acted greedily. So here's what Q-learning looks like when we put it all together. Luckily, it looks quite similar to the prediction problem pseudocode. First, we are given some environment object. Then we initialize Q with random values. Then we enter a loop that goes for a predetermined number of episodes. Optionally, you can keep going until Q or the policy converges. Next, it's the same as what we had before. We reset the environment and start back at the initial state. We initialize the done flag to false. Then we enter a loop for the episode, quitting only when we are done. Next, we use epsilon greedy to choose an action. Then we take a step in the environment. We get back the state S prime, the reward R, and the done flag. Next, we create the target for the Q update, taking the max over Q given the state S prime. Next, we update Q of S and A using the target we just calculated. Lastly, we update the current state S to be the next state S prime. Finally, when we exit the loop, we have found the optimal policy. Let's summarize what we just did, since that was pretty long. First, we started by noting that Monte Carlo will not work for infinitely long episodes, and that it's problematic in that we have to wait until an episode is over in order to do any learning. Instead, we make use of the fact that the return can be defined recursively. This allows us to approximate the return using only the next reward and the value at the next state. We also learn that reinforcement learning ultimately starts to look like supervised learning, where our target is not a real target, but rather an estimation made by our own model. We are essentially doing gradient descent on a Q table. Using this approach, it allows us to update our Q table on every step, because we only have to wait until we receive a single reward to make an update. We call such an approach online learning because the agent learns while it collects data.